start. Hilbert Space. H consists of a set of vectors psi, pi, j, and so on, and a set of scalars A, B, C, so on, which satisfy the following four fundamental properties. These properties are: first, the Hilbert space should be a linear vector space. That is, first of all, the Hilbert space should follow the properties of linear vector space, that is, it should have the set of elements like vectors and scalars, and it should follow the two algebraic rules of addition and multiplication. Second, the Hilbert space H has a defined scalar product which is always positive. So it should have a defined scalar product. I underline it. It is a defined scalar product, and this scalar product is given as see if the if the scalar product of an element psi with another element phi, then it is defined as and denoted by psi comma phi in bracket, and it is like psi phi. This scalar product is always a complex number. So the defined scalar product is such that if the two elements psi and phi are there, and we want to get the scalar product of these two elements, which is denoted by in bracket psi comma phi, and it is always a complex number, and it is complex number and scalar. Obviously, it should be scalar, and this scalar product also satisfies the following properties. The first properties of the scalar product of the Hilbert space is if we want to get the scalar product of psi and phi, as you know, denoted by psi comma phi, is such that psi comma phi is always a complex number and is a scalar and is equal to the complex conjugate of the scalar product of phi with psi. So point is that this scalar product psi with phi is equal to the complex conjugate of the scalar product of phi with psi. So here the sequence of psi with phi is equal to the complex conjugate of phi with psi, which is equal to now the next properties of the scalar product is that the scalar product of psi with phi is linear with respect to phi. That is, if we have psi and phi is such that phi is equal to a phi 1 plus b phi 2, then the scalar product of psi with phi is given by scalar product of psi with phi, that is equal to a phi 1 plus b phi 2, which can be equal to scalar product of psi with a phi 1 plus scalar product of psi with b phi 2, which gives a scalar product of psi with phi 1 plus b scalar product of psi with phi 2. So ultimately we get scalar product of psi with phi, where phi is given in the terms of addition of the a phi 1 and b phi 2. So we get the scalar product of psi with phi as a linear, which we can see that if we are getting the scalar product of phi with psi, then it can be written as a phi 1 plus b phi 2 scalar product of psi, which is written as a star phi 1 with scalar product with psi plus b star phi 2 and scalar product with psi. So you can see that this is different than this. That is, if we change the sequence of phi and psi, the linearity property vanishes, that it becomes nonlinear. That is, the scalar product of the Hilbert space is strictly linear with the phi if phi is written as a phi 1 plus b phi 2. The next properties of the scalar product is if we get the scalar product of a state vector psi with itself, then it is always positive real number. That is, scalar product of psi with psi is equal to nothing but psi star psi, that is equal to the norms of psi square, which is always greater than equal to 0. Where equality holds true only for psi is equal to 0. That is, if psi is equal to 0, then we get the psi and psi scalar product is equal to 0. Unless until psi is equal to 0, we can't get the scalar product equal to 0. We will always get the values more than 0. The third properties of Hilbert space is that H is separable. What does it mean? H is separable. It means that in the Hilbert space, there always exists a Cauchy sequence. There always exists a Cauchy sequence psi n belonging to Hilbert space H, where n is equal to integer 1, 2, 3, so on, such that for every psi belonging to Hilbert space H and a positive real number, epsilon greater than 0, there exists at least one vector element psi n of the sequence for which psi minus psi n is less than epsilon. That means in the Hilbert space there exists a Cauchy sequence. That is, if we if we are proceeding further, the next element becomes closer to the preceding element, and so on. That means for every element of the Hilbert space, there exists a coming element in in the sequence such that their difference is always a positive number, that is always less than epsilon, which is greater than 0. Hence the Hilbert space is separable. Now the fourth property of Hilbert space is that Hilbert space is complete. That is, it shows the completeness. What does it mean? This means that every Cauchy sequence of elements psi n belonging to Hilbert space H converges to an element of this Hilbert space H. That is, every Cauchy sequence converges to an element of H. That is, for any psi n, the relation limit n m tends to infinity psi n minus psi m norms is equal to 0 defines a unique limit psi of h such that limit n tends to infinity psi minus psi n is equal to 0. So Hilbert space H is complete as every Cauchy sequence of elements in Hilbert space converges to an element of this Hilbert space. So we see that Hilbert space has four fundamental properties, that is, a Hilbert space is a linear vector space, Hilbert space has a defined scalar product, Hilbert space is complete, and Hilbert space is separable. So friends, these are all the things that we learned in this video lecture about the Hilbert space. If you like this video lecture, please press the like button and share it with your friends. And if you have any comments regarding this video lecture, or if you have any other queries, please let us know by providing comments in the comment box so that we can update regarding that comments. Thank you, friends. Please stay tuned and subscribe the Sci Academy channel.